chemistry. Nuclear chemistry involves reactions that we're really only talking about the nucleus. So what's inside the nucleus? We have protons and neutrons. Now when we think of nuclear, we are thinking of radioactive decay, and radioactive decay happens when the nuclei of an atom is unstable. So in order to gain stability, it has to release protons and neutrons. Now this process actually creates a lot of energy. There's two different types of decay that we are going to talk about. We're going to talk about fusion and fission. Both of these create very extensive amounts of energy. Fusion is what happens in our sun. So we know that our sun and stars, all the other stars, are very hot. Basically they're balls of fire, and they get all that energy from fusion. Fission is what we use in order to create nuclear power, all of our renewable energy sources. So, that will also create a lot of energy. Now let's talk about the difference between these two. Fusion is the combining of two nuclei to form one. Think of the word fuse. You know that fusing two things together means you have two things, you're making them one. Same thing here with fusion. An example of this, like I said, is in the sun. Now, let's look at an example here. So instead of balancing out molecules, we're balancing out nuclei. So we know that the bottom number over here is our atomic number, which is the number of protons, and the top number is our atomic mass for this particular isotope, and we know that our atomic mass is our protons plus our neutrons. So here we're going to be fusing together a helium and a beryllium, and we're going to be creating carbon. Now, how do you know it's this carbon? Now this is pretty simple, so just follow along and I think you'll pick up on it pretty quickly. Whenever we are doing chemical reactions, we had to make sure that our reactants was balanced with our products. Now here we're going to be doing some balancing, but we're not balancing coefficients. Instead, we're balancing the number of protons and neutrons present. So basically we're balancing the mass and the number of protons, because those are the numbers that are represented here. So if I'm fusing together 4,2 helium and 8,4 beryllium, 4 plus 8 equals 12, 2 plus 4 equals 6. And then how do I know this is carbon? Well, I know my atomic number, so I'm just going to look up on my periodic table which element has an atomic number of 6, and that is carbon. So fusion, we're only talking about a general sense of fusion. Now, if we're talking about fission, there are going to be many different types of fission. And fission is kind of the opposite of fusion. Fission is radioactive nuclei breaking down into multiple nuclei in order to become stable. Now, when fission occurs, an example of this, like I already said, was nuclear power plants. When fission occurs, you have a nuclei that's going to break off into multiple different nuclei. Now, there's 4 different types of fission that we're going to be talking about. Each one of these different types of fission, one of these particles or wavelengths will be one of the products that's being broken off. But there are going to be other products, and that comes with the remaining part of the element, of the nucleus that's left over. It's going to form a new nuclei with a different number of protons and a different number of neutrons. So the first one that I want to teach you is alpha decay. So alpha decay is when a helium nuclei gets shot off of whatever the nuclei is. So it's always going to be 4,2 helium. That's your alpha particle. You do have to remember what that is. And this is going to be one of our products. The next type is our beta decay. And same thing, an electron. Now when we're talking about nuclear, we call it a beta particle, but it really is the same thing as an electron. A beta particle is going to be shot off of an existing nucleus. Now gamma is not an actual particle. It is instead a wavelength of light. And so it's a very extremely high energy light. And it has a 0, 0, and it has like an upside down ribbon. Now the last one is a positron. And now a positron, it's not a proton. It has the same mass as an electron, so a very extremely small mass would be almost considered 0. But instead of it being negative, it's in turn positive. So simplify it here, it's kind of the positive form of the electron. Now, all of these are different type of nuclear decay, and if we have radioactive substances, we know that they give off radiation. Now, we have to protect ourselves from these radiation particles, so what we want to do is figure out how we can protect ourselves. So alpha particles are going to be the least dangerous, and all you need to protect yourself from alpha particles is either paper or air. Okay, so you can be protected from alpha particles pretty easily. Beta particles. Now, beta particles give off a little bit more radiation, so you're going to need something a little bit stronger in order to protect yourself. Here, we can use plastic or aluminum to protect ourselves. Gamma, I said, was a very high energy wavelength, so you're going to need something even stronger to protect yourself. Here, we can use either lead or cement. And positron we don't really need to worry about. We're going to worry about how to protect ourselves from alpha, beta, and gamma. Now let me show you how to do some equations with these. Let's start off with our alpha decay. So a problem that you can get is saying that you're starting off with 21084 polonium, and it's telling you that it's alpha decay. So you have to know that alpha decay means that you are emitting a helium nuclei, and then we have to figure out what the other nuclei is going to be. So in order to do that, we know that our protons and our mass number have to be equal. So we're starting off with 84 on our reactant side. So we have to say 84 minus 2 equals 82. That's going to be the number of protons of our additional nuclei. Now we have to figure out the mass number, so we have 210 minus 4. That's going to come out to 206. So that's going to be the mass number of our new nuclei. And like I said before, you're going to look up 82 on your periodic table, and you're going to figure out which element or which nucleus that belongs to. So I'm going to find 84. Oh, sorry, I'm going to find 82, and that is going to be lead. All right, let's do the beta decay now. So beta decay, we can start off with carbon 14. And since it's beta decay, we're going to release a beta particle. So that's 0 minus 1 E. Then we have to figure out what's remaining. So 6 minus negative 1 is going to give us 7. 14 minus 0 is going to leave us with 14. And then we're going to go to our periodic table and figure out which has the atomic number of 7. And we're going to see that that is nitrogen. All right. Let's go on to gamma. Now, for our gamma radiation and our gamma decay, it's usually going to be paired with another type of decay. We're not usually going to see it by itself. And a lot of that has to do with, it's because you have a light that's being forced off instead of an actual particle. So an example here is 238 uranium. Is going to decay, and I'm going to tell you it's going to be an alpha and a gamma decay. So if it's alpha and gamma, that means we're giving off both an alpha particle and a gamma particle. So we have to figure out what's left. So we have 92 minus 2. That gives us a proton of 0. 238 minus 4 minus 0, that's going to give us 234. And again, you're going to look up 90 on your periodic table, and you're going to realize that you have thorium. Last type that we're going to do is our positron. So we are going to start with 3819 potassium. I'm going to tell you it's positron decay. So you know that you have a 0, 1, E. We just have to figure out what's left. So 19 minus 1 leaves us with 18. 38 minus 0 is 38. We go to our periodic table, look up which nucleus has